Today we'll be going over quadratic key features. We're going to identify, label, and draw the key features of quadratic functions given the equation in standard form. Now what we mean by standard form, we are going to have the x squared and x set always, and we're going to have a value a, b, and c given. Now, before we get to an actual example of one of those equations, we're going to start labeling two examples of parabolas. In this case, the dotted line represents where our parabola changes direction. This is what we call the axis of symmetry, which I'm going to shorthand as AOS. Now what this dotted line is showing, is, say, for our first parabola, it is going down if we start from left leading to right until it reaches this dotted line. Once it reaches this dotted line, it changes directions and starts going upwards. Our y values increase. This is where it mirrors itself across the dotted line, our axis of symmetry, thus giving it its name. And the same on the second parabola. We start left to right, we go up until we hit the axis of symmetry, and it mirrors, making our function values decrease. Now the point at which it actually changes direction, the minimum or maximum value, is our vertex. Now it doesn't matter if it is a minimum or maximum, as long as it is changing direction, it is a high or low point, we can call it our vertex. Now, the rest of the key features, our x-intercept and our y-intercept, are the same. Our y-intercept is where it crosses the y-axis. And our x-intercept is where it crosses the x-axis. Now, you learned from an earlier lesson that quadratics can have a maximum of 2 x-intercepts and a minimum of 0 x-intercepts, depending on the location. Now, using this an example, we're given the equation y equals x squared minus 4x plus 5. I went ahead and already plugged in the values that we can get from a calculator. This showing our input of -1, we would get an output of 10. Input of 0 gives us an output of 5, 1, 2, 2, 1. This only lists the points. This does not list all the values in between. Since this is a function, it includes everything. So, for example, on my graph to the right, I listed the points, but I didn't show the full function. It includes everything in between those points, which we show with solid lines. Now, with our graph shown and our table shown, we can see the point where it changes direction on the table. Notice at the y value 1, the numbers around it are the same. This shows that we decrease until we get to the value 1, and then we start increasing. That is our change in direction, our change in values. On our graph, we notice that this is the lowest point, which is our change in direction. So this will be our vertex, the location 2, 1, or you can look at the graph. Now remember, with locations, we separate our x and y value with a comma, and we put parentheses around it to show it as a point. When dealing with the axis of symmetry, it is the line at which our function starts changing direction. A line at where the vertex is. So in this case, any vertical line is always a x equals. The y value can be anything, but our x value can only be one value. In this case, our x value, our x equals, is the vertex x value, 2. Our x can only be 2, where our y value can be anything. This is shown with the equation x equals 2. Now in this case, we have a choice. We can either state that this is a maximum or a minimum. Since this has a low point, a valley, this is going to be a minimum. It will never get lower than that point, our vertex. Now, because we are dealing with continuous functions, that's what this quadratic is. There is no limit on our x values. We can use all real numbers for our domain, but our range is limited. Starting from left to right, we go down until we reach a value of 1. So we know that the lowest value that this can be is 1. And it increases forever. Now what I did here was I was already setting up for my next part, but this would say that it goes on for infinity. But since it goes on in one direction forever, we only have to state that it is greater than 1. And I wrote the wrong letter too. Range is dealing with y, not x. And we know that it has to be greater than 1. Since this is a single inequality, I only need to write the 1. Now, the next example I'll go through a little bit quicker because we do have an example. Yet again, I put in the information that you could just plug into a calculator, our TI-84s. We have videos on that as well. But we get -2, -9, -1, -4, 0, 1, 1, 0, 2, -1, 3, -4, and 4, -9 as our values, our locations. Yet again, there is nothing limiting this. This is a continuous function. So we are not just drawing the points listed on the table, but every point in between as well. We show this with a continuous line. This time we notice that we have a high point. So we already know that we're looking at a maximum. But just to follow the order, we want to find our vertex first. That's where it changes direction, our maximum or minimum point. For our table, that is when our numbers change direction. We notice that we're going up in value, reach a 0, and then we start going back down. The numbers repeat themselves around the 0. So in this case, our point 1, 0 is the vertex. For the graph, same thing. We start from left to right. We go up, reach the point 1, 0, and then we start going back down. We change direction. Our axis of symmetry still uses the equation x equals. In this case, it is still our vertex x value. Which our x value was 1. We stated that this was a max value already. It is the highest point of this function. The arrows show that it goes down on both ends, so there is no minimum. Our domain for this setup is still the same. These arrows are going mainly downwards, but they are going outwards. That's why we can use any value for x, all real numbers. Now, your range for this one is flipped. We don't have our y values greater than the point. Because this is a maximum, our y value is going to be less than a given point. Less than or equal to, I'm sorry. That goes for the other one as well. This is not greater than or equal to 1. This is greater than or equal to. Since this is a solid line at the vertex, that is including the point. That's why it is going to be or equal to as well. In this case, the highest point is a y value of 0. So we can state that the range is any y value greater than or equal to 0. So to recap, our vertex is simply the point at which our function is changing direction. It can be a minimum or a maximum value depending on the direction of our parabola. The axis of symmetry is the line in which the parabola reflects itself. It is the line where it changes direction. If they're going down, it's going to go up, and then vice versa. If it's going up, then it would go down at the axis of symmetry. For the most part, our domains for parabolas are going to be all real numbers. I can plug in any value for x, and I will find some number. Now with parabolas, they increase significantly more in our y values than they do for each x value given. So we won't see where they cross at -10 or +10, but we know that we can still use those values for x. Whereas for our range, it's limited to where our vertex is. Vertex being 0, we use the value 0. Or our vertex y value being 1, which limited us to the 1 value. Then the symbol that we use, depending on which way our function is moving. All of my y values are greater than or equal to 1, so I use greater than symbol for minimums. And then for maximums, I use the less than or equal to. All my values go below or equal to the y value 0.